last lecture, we have discussed about concept of hydrogen bonding. Now, in today's lecture, we will be discussing about important concepts of organic chemistry, that is aromaticity. Aromaticity is helpful to explain and understand the properties and reactivity of benzene and whole class of its derivatives. This is very important property and in fact unusual behavior, extra stability shown by the unsaturated compounds. These compounds are benzene, naphthalene and a whole lot of their derivatives. Characteristics of aromatic compounds are, these are cyclic compounds having alternate double bond. They resist addition and oxidation reactions in spite of having high degree of unsaturation. They have low heat of hydrogenation and combustion. So, we can see that these compounds are quite stable and in spite of having conjugated double bond, number of double bond, they are not unstable as polyenes. They show electrophilic substitution reaction. They does not show addition reaction usually, but they show electrophilic substitution reactions more, and because of these electrophilic substitution reactions, they are able to prepare nitrated, halogenated or sulfonated products. Many theories have been put forward to understand and explain the aromatic character of compounds. Most important ones are being discussed here. MJS Diwar have presented a theory named as resonance theory. According to this theory, compounds with alternate double bond possess very high resonance energy and thus they are quite stable. But this theory was not able to explain stability shown by all the aromatic compound or instability shown by many compounds who possess alternate double bond but they are not aromatic. Next theory, which was presented by Robinson and Armitt, was based on aromatic sextet. So, according to this theory, if 6 pi electrons are present in the ring, then compound will be stable. This theory was not able to explain stability of compounds having 2 pi electrons or 10 pi electrons like naphthalene and many more. Therefore, finally, most accepted theory was the theory put forward by Erich Huckel, which is popularly known as Huckel's rule. He made his significant contribution in the field of organic chemistry, which is basically very much dependent upon benzene and its derivatives. According to this theory, conditions of the aromaticity are, first of all, it is necessary that a compound should be cyclic and planar. As we know, because of the planarity, it should have each atom of the ring in sp2 hybridized state, because in case of sp3 hybridization, compound will not be planar. Most important rule of this theory was the 4n plus 2 pi electron system. So, if that particular compound possesses 4n plus 2 pi electron delocalized in the ring, then that compound will be aromatic, otherwise not. Here we can see by putting value of n to 0, we will get the value 2. So, compound with 2 pi electron will be aromatic. In the same way, if we put value of n to 1, then compound will have 6 pi electron. So, these compounds having cyclic planar molecule with sp2 hybridized each atom of the ring and having these values as delocalized pi electron will be aromatic in nature. But if a compound satisfies first condition and second condition, but it is having 4n pi electron system, then compound is said to be anti-aromatic. Now we will discuss some examples of aromatic compound. This will help us to understand this theory. Simplest and first example and most important example is that of benzene. Here we can see 3 pi bonds are there. So each pi bond is associated with 2 pi electron. So 2 pi electron here, 2 pi electron here, 2 pi electron here. These together make 6 pi electrons. Here we can also see these pi bonds are present alternate position. Because of their presence at alternate position, each atom of the ring will be sp2 hybridized and compound is cyclic also. Therefore, benzene is aromatic. It satisfies all the 3 conditions put forward by the Huckel's rule. Now take the another case. This is example of cation, cyclopropenyl cation, which possesses 2 pi electron because of the presence of this pi bond and nothing more. Here we can further check the sp2 hybridization of each atom forming the ring. We know because of the presence of double bond, this atom will be sp2 hybridized. In the same way, this will also be sp2 hybridized. Here we can see the positive charge. So this is more like a carbonium ion. And we know that because of the carbonium ion, this carbon will be in the sp2 hybridized state. So all the atoms forming the ring are in the sp2 hybridized state. Ring is cyclic and it is having 2 pi electrons. So 4n plus 2 rule is satisfied and this compound is also aromatic. We can further understand this theory with the help of these examples. Here we can see 2 pi electrons, 2 pi electrons here, so 4 electrons. Here this is in the form of carbon ion. So negative charge is associated with lone pair of electrons. So 2 electrons here, 2 here and 2 here. Together 6 pi electrons are present. And each carbon atom of the ring we can see here also because of the presence of this negative charge on alternately present double bond, this will also be in the sp2 hybridized state. Therefore, this compound is aromatic in nature. This is case of naphthalene. We know here also it is very clear from the diagram that total 5 double bonds are there. So, all the 3 conditions of the Huckel's rule are satisfied and compound will be aromatic. Their properties also show the normal behavior shown by the aromatic compounds. They are quite stable. Now we will discuss the case of some other type of compounds where elements other than carbon are also present as a part of the ring. These are called heterocyclic compounds where elements like nitrogen or oxygen are part of the ring. Here we can see because of this double bond and this double bond 4 pi electrons are there and this electron pair, so total 6 pi electrons are there. In this case also it is clear that 2 plus 2 plus 2 total 6 electrons are there. This example we can understand in more detail. Here we can see this is the orbital diagram of pyrrole. Each atom of the ring is sp2 hybridized. So unhybridized orbital present on each atom. Here we can see these unhybridized orbital are participating in the delocalization of electrons. Here we can see one electron is here, one is here, one is here, one is here. This is just like benzene except here. Here we can see on nitrogen atom this lone pair is present in the unhybridized orbital. So this is lying parallel to rest of the orbital. Therefore this electron pair will be delocalized with rest of the ring. So total 6 pi electrons are present. Now we take the example of furan where we can see on oxygen atom 2 lone pairs are present. One of the lone pair is present on the unhybridized orbital so that it is participating in delocalization and it is contributing towards 4n plus 2. But other electron pair is present on the sp2 hybridized orbital. Therefore, it is aligned outside the ring and it is not participating. So we can get here again 6 pi electrons, delocalized, cyclic compound, and each atom is sp2 hybridized. Hence, all the conditions are satisfied. Now we can further understand two more examples of heterocyclic compounds. In case of pyridine, this is different than pyrrole. In case of pyrrole, we have seen that this lone pair was present in the unhybridized orbital. Therefore, it was contributing towards 4n plus 2 pi electron. But here we can see this lone pair is present outside. Here also we can see that this lone pair is not participating with the delocalized orbital. Here we are getting 6 pi electrons with the help of these 3 pi bonds. So total 2 plus 2 plus 2, 6 pi electrons. Each atom is sp2 hybridized. Therefore, pyridine is also aromatic in nature, though its lone pair is not being delocalized with the ring. In case of pyrimidine also, this is very important compound in biochemistry also. We can see here again these lone pairs, this lone pair and this lone pair, they are not participating in the delocalization. They are present outside the ring. But we are getting a total of 6 pi electron, one from each orbital. Here we can see ring is 6 membered. So one from each orbital, and thus in this way we are getting total 6 pi electrons. Each atom is sp2 hybridized and compound is cyclic also. After discussing the case of aromatic compound, we can also understand some of the non-aromatic compounds. Non-aromatic means they are cyclic, but they does not have all the conditions proposed by the Huckel's rule. For example, we can see this case, it possesses 2 pi electrons, 4n plus 2. It is cyclic, but here this compound is not planar because each atom of the ring is not sp2 hybridized. Here we can see this particular carbon, it is having 4 single bond. So 4 single bond means sp3 hybridization. In this case also, we can see this particular carbon is singly bonded and 2 hydrogen atoms are present here also, which are not being shown. So this particular carbon atom will be sp3 hybridized. So even if they possess 6 pi electron, compound is cyclic, but compound is not having each sp2 hybridized carbon atom. Therefore, they are not aromatic, but they are known as non-aromatic compounds. To discuss further, we will take the examples of anti-aromatic compounds also. These compounds are again cyclic. They possess each atom of the ring as sp2 hybridized atom, but not 4n plus 2 pi electrons. Here number of pi electrons are followed by 4n pi rule. This is the case of cyclobutadiene, where we can see 2 pi electrons here and 2 pi electrons here. So a total of 4 pi electrons are present. Cyclobutadiene is in fact very unstable compound. This is smallest aniline and its lifetime is very short and shorter than even 5 seconds. This is highly reactive even at minus 78 degrees Celsius. So we can see that at this much low temperature also this is capable of reacting. So it is not aromatic but very unstable anti-aromatic compound. Here we can see how it is being dimerized. These are 2 units of cyclobutadiene molecules, and at this low temperature they are reacting with each other. This reaction is known as Diels-Alder reaction, very popular reaction, and this adduct is being formed. Another example of anti-aromatic compound is example of cyclooctatetraene. As the name suggests, this compound will also be cyclic, having 8 member in its ring and presence of 4 double bond. But here these 4 double bond which are giving us 8 pi electrons, these electrons are not delocalized but they are localized pi electron. Why they are localized? Why they are not being delocalized? This is because of the formation of non-planar molecule. Here we can see its shape is tub-like structure. So because of the formation of this non-planar molecule, this is not able to delocalize its 8 pi electrons. Therefore, this compound gives normal addition reactions shown by the polyenes. Now, question arises, why this 4n plus 2 rule only? Why some other number? Is there some magic in this 4n plus 2? Yes, this can be understood with the help of this theory. In case of cyclic conjugated molecules, always there is a single lowest lying MO is formed, above which MOs lies in degenerate pairs. So, single lowest MO, so we will be needing 2 electrons to fill that single lowest MO. Then come the degenerate pair of MO. So, to fill up the degenerate pair of MOs, we will be needing additional 4 electrons at each step. So, because of the need of this additional 4 electrons at each step, this 4n plus 2 number is calculated. Completely filled MOs will stabilize the system and hence we can expect the unusual stability shown by the aromatic compounds. We can further understand this thing with the help of this diagram of the benzene. Benzene is the simplest example. Here we can see 6 carbon atom possess 6 unhybridized p orbital. On each p orbital there is 1 electron present. So, together they are contributing 6 electrons. Since 6 p atomic orbitals are combining together, so 6 MOs will be formed. 3 will be in the bonding and 3 will be the antibonding. But as we have learnt now that there is always the single lowest lying MO which will be filled by 2 electrons and above which MOs lies in the degenerate pair. Degeneracy means these 2 orbitals will possess equal energy. Therefore, they will be filled in this fashion. 1 electron will fill up here, then 1 here, then 1 here, then 1 here. So, in this way we can see all of the 6 electrons are present in pairs here, thus giving stability to the system and hence compound is aromatic. We can discuss the another case of cyclopentadienyl anion. Here this is the case of anion, this is the case of radical and this is the case of cyclopentadienyl cation. Out of these 3, only cyclopentadienyl anion is extra stable and hence termed as aromatic. Why this aromaticity? We can calculate here 2 pi electrons here, 2 pi electrons here and 2 electrons because of the presence of this negative charge making it anion. So, together 6 pi electrons are here. Here we can see only 2 plus 2 and 1, 5 electrons are here and in this case only 4 pi electrons are here. Let us see the orbital diagram of these 3 compounds. Here we can see how the 5p atomic orbitals are combining together. So, we are combining 5p atomic orbitals, therefore, total 5 MOs will be formed, but they will be formed in a way that one single lowest lying MO, then MOs in the degenerate pair. Now, we will fill up the electrons. In case of this cyclopentadienyl cation, where number of electrons are 4, we can see these 2 electrons lie unparalleled. Therefore, this will not be stable. In case of radical, we get an extra electron, but here again this electron remains without pairing. But in case of cyclopentadienyl anion, we are getting completely filled degenerate orbitals, therefore stability, and cyclopentadienyl anion is aromatic in nature. Another rule, which is equivalent to Haeckel's rule, has been used to explain and understand stability of aromatic compounds. This rule is known as polygon rule. Rule is based on relative energies of molecular orbitals of conjugated system. Here we can see this dotted line represents the non-bonding MOs. This dotted line passes through middle of the polygons and each vertex represents one pi molecular orbital. Molecular orbitals lying below this dotted line are called bonding molecular orbitals, and molecular orbital lying above this dotted line are called anti-bonding molecular orbitals. Electrons are filled up in the increasing order of energy, and here we can see in case of benzene, which possess 6 pi electron system, only bonding MOs are filled. Therefore, benzene is aromatic in nature. Cyclobutadiene and cyclooctatetraene, here non-bonding MOs are also occupied, and these two are called anti-aromatic in nature. So, today we have learnt about very important and interesting concepts of organic chemistry, aromaticity, which is most important concept of organic chemistry. We have learnt various theories which have been put forward time to time to understand the aromaticity. We have learnt about 4n plus 2 Haeckel's rule, how this 4n plus 2 magic number has evolved. So, all these concepts are very important for a beginner to know about the chemistry. Thank you.